All right, hi everybody. Welcome back. So let's see, if I remember right, we were last time just finishing up the set of notes on continuous modeling with continuous random variables, and we had just introduced power law distributions. So I wanted to review those and talk a little bit about how to recognize those when you see them. And then we can move on to the topic for today, which is regression. All right, so power laws are distributions over positive numbers. They're based on the statistic, which is the log of the number that you see, and they have a probability density that looks like a negative power of x. And that negative power has to be bigger than 1, otherwise you can't integrate the density because the integral of 1 over x is infinite. And it's called the power law because of this functional form, right? The dependence is just a power of the random variable. There's a lot of different natural distributions that people claim follow power laws. Things like the total amount of energy released in an earthquake or the total amount of property damage due to a big storm. One of the really important properties of a power law distribution is what's called a heavy tail. A heavy tail means that extreme values of x are still fairly probable. Obviously, the more extreme you go, the probability has to decrease, otherwise you wouldn't be able to integrate the distribution. I mean, it could increase for a little while, but it has to decrease eventually. But heavy tails are actually a pretty important phenomenon in practice. You really have to model them if your distribution has them. Otherwise, you're going to have, well, you'll greatly underestimate the probability of extreme events. So in particular, in a power law distribution, the probability goes down only 1 over polynomial in x, whereas if you compare that to some of the other distributions we've seen, a normal distribution has much lighter tails. The probability goes down as e to the minus x squared, which is like blazingly fast compared to polynomial. You can see that by just plotting it on a like on a log-log plot, which we'll show later. All right, the CDF of a power law looks like this. It's basically just the rule for integrating a polynomial that you've seen before. So in particular, 1 minus the CDF is also a power law, but with a different exponent. It's theta minus 1 instead of theta. And let's see, so this is a continuous power law distribution, but it also makes sense to define a discrete one. So you could have one over the, let's say, the positive integers if you wanted to. And that would make sense to define, for example, a distribution over word counts. So if you look at a document, like a very long document in natural language or a collection of documents, if you sort the words by how frequent they are, the distribution of the kth most frequent word looks like it follows a power law. So, like I said, it's important to identify this sort of power law or heavy tail behavior in distributions if it's present. So a good way to do that is with a log-log plot. So to do that, so you remember we had other plots that we talked about, like QQ plots, to compare to a specific distribution. This compares to the entire class of power law distributions, which is pretty useful. So what we can do is, well, so if you want to identify a polynomial in general, like x to the k, then you can make a log-log plot. You plot, if y equals x to the k, then if you plot log y versus log x, the relationship will be a straight line, and the slope will be equal to k. Right? That's because the log of x to the k is k log x. And so to identify a power law distribution, what we can do is estimate its CDF empirically. For example, we can use kernel density estimation like we defined before. And you can make a log-log plot of x versus 1 minus the CDF of x. And if you have a true power law, it'll look something like this, right? So if the parameter is theta, we'll get a line with slope minus theta minus 1. And this one is based on a sample of 100 points from a power law distribution with theta equal 2. So the slope here is minus 1, which is minus theta minus 1. And you can see the red line is exactly that slope, and the blue line is the estimated CDF that we get. I think I used a piecewise linear CDF in this case. Let's see. So one of the things to note is that at the top left, that corresponds to small values of x, or probable values of x. And the points there are bunched quite closely together, and the line tracks quite closely. The blue line tracks the red one quite closely. As we get down to the right half of the plot, the bottom right half, there's many fewer samples, right? This is based on the rare values, the rare extreme values of x. And so the relationship is a little bit noisier here because it's based on less data, but that's okay, right? You expect to see a little bit of departure when you're looking at the part of the plot that's estimated from only a few samples. All right, so that's a log-log plot. And like I said, it's really useful for identifying when you have power law distributions, which is one of the common ways that you'll see a heavy tail in your distribution. All right. So I've talked about some common families of distributions, discrete, continuous, right, a bunch of different families. If you have a variable that doesn't quite follow one of these distributions, it's often useful to make a transformed random variable that does. So for example, you could take your random variable x and change it to x cubed. And maybe if x isn't normal, then x cubed is normal. Or maybe you take you have a positive variable and you take its log. And maybe the positive variable didn't have a nice distribution, but when you take the log, it's normal. And so if you can find the right transformation, that makes it a lot easier to model things. And so what people will do is they'll search for, they'll try a few common examples of transformations and then use something like a QQ plot to check whether they've got the right answer. It turns out that you can transform any density into any other density if you're given the CDFs for both of them. And the way that works is basically, so the simplest example is suppose that you have a uniform random variable u and you want to transform it to have a given CDF f. So if you define x to be f inverse of u, it's pretty easy to see that the distribution of x is the one that's desired. And the reason that that works is right here. So the probability that x is less than or equal to some cutoff little x, well, we can take the same transformation of both x and little x, so f of x and f of little x. F of x is by definition u, right? So this is the probability that u is less than or equal to f of x. And the probability that a uniform random variable is less than or equal to any number between 0 and 1 is just that number. Right, and so we get that the CDF of x, the probability that's less than a cutoff, is capital F of x, which is what we were hoping for it to be. Okay, so now we've shown how to transform a uniform random variable into any other distribution. If we apply f to both sides of this equation, we get that f of x is equal to u, right? Which means that we can take a random variable x, and by applying its CDF, we get a uniform random variable. And so that gives us the recipe to transform any random variable into uniform, and uniform into any random variable, right? Any desired CDF into a uniform random variable, and any uniform random variable into any desired CDF. So if we want to go from one CDF to another, we just apply the CDF to get to uniform, and then apply the inverse of the other CDF to get to the desired CDF. So if we have if X has a CDF F and we want the CDF to be G, we take G inverse of F of X, and that'll have the desired CDF. All right. So that's the end of the notes on different families of distributions that we might use to model single random variables. And we also talked briefly about multiple random variables as a vector. So we have now a whole bunch of choices for how to model a given variable. And the question is, how should we choose which one of these models to use? So for example, if we have a given random variable, how do we decide whether to model it as Poisson or binomial or normal or power law or whatever, right? So there's a couple of ways to do that. One of them is to see if there's a theoretical reason why it should be a particular family. So for example, if you know that your random variable X is the sum of a whole bunch of small contributions from different sources, then the central limit theorem tells you that, well, probably normal is a good model for X. Or if you're modeling a probability, well, a beta distribution or a Dirichlet distribution are reasonable choices. Another is to use plots, right? So you can use the QQ plot, you can use the power law plot to confirm a guess, or just try a whole bunch of things and see if one of them seems right. And then the last thing is transformations, right? So you can take a random variable that doesn't fit one of the known distributions and make it transform to bring it closer to one of the known distributions. And then finally, if it, through all of these tricks doesn't match a known distribution, then you can use something like maxent to try to build our own family. Or in the univariate case, we can fit a CDF to it by something like kernel density estimation. All right. So somebody's asking for more information about what a heavy tail means. So let's think a picture is the right way to do this. So we have a random variable, we'll call it X, right? And so we'll plot X on the horizontal axis and the probability of X, or if it's continuous, the density of X on the y-axis, right? So it'll do something or other out at the beginning, and then since if it goes, if the largest possible value is infinity, eventually the probability has to start decreasing, because if it didn't, then you couldn't have it sum or integrate to 1. So this part here, this is called the tail of the distribution. And then this part here is called the body of the distribution, right? And you can have the same thing for a distribution that can, go to positive and negative infinity. So if you have a, something that looks like that, right? You have a tail here, another tail on the other side, and then in between is the body. Right, so tail just means the part of the distribution that you get to when you go off to infinity or to very large values. And so heavy tails means that there's a lot of probability mass in the tails. So you could compare a couple of good examples, right? So if you compare normal, where the tails are proportional to e to the minus, let's say it's a standard normal, so the tails are proportional to e to the minus x squared over 2. versus, you haven't seen this before, but there's something called a Cauchy, C-A-U-C-H-Y, and the tails are proportional to 1 over 1 plus x squared, right? And so if you look at those two, right, if you go off towards infinity, e to the minus x squared goes down really, really fast, right? Like if you're above, x equals, let's say 7 or 8, you're going to have something that's 0 according to your floating point representation. Versus a Cauchy, where, x squared, 1 plus x squared does grow as x gets bigger, but it doesn't grow nearly as fast. Nothing close to exponential even. Nothing close even to singly exponential, right? And this is e to the minus x squared, right? So that's even worse than exponential. And so you can see that the Cauchy has far heavier tails than the normal does. All right. So that's the end of modeling. Or at least the end of the notes on modeling, and I think we can move to the next topic. So we're going to talk now about conditional models. So what is a conditional model? So suppose we have two variables. For now, let's just say they're both real numbers, and we'll call them x and y. I mean, there could be multiple x's and multiple y's, but it's enough for now to think of a single x or y. And so we could write the joint probability, right? This is just the chain rule for probabilities. The joint probability is the marginal of x times the conditional of y given x, right? And so a conditional model means that we're going to only try and spend our effort modeling the second term, p of y given x. And that means that we don't need to spend the effort, the mental effort, to come up with a model of p of x. So a conditional model like this is useful if we never have to predict x itself. We're always given x, and then from x we want to predict y, right? So it might be, for example, that a patient walks into the clinic, and the patient always tells us their, height, weight, age, that sort of thing, all of their sort of simple features, and we want to predict some medical outcome from these variables. We never have to predict the age of the next person who walks into the clinic. Instead, we only have to predict some medical outcome y from those variables. So a model of this conditional distribution is called a conditional model, in contrast with a model of the joint distribution, which is called a joint model. There are other names for these as well that you might see. So a joint model is sometimes called a generative model, because if we have the joint model, we can sample from it to get x's and y's. We can generate pairs, new pairs. While if we have a conditional model, we can't. We have to be given x, and then we could generate y. And then if the thing we're predicting, y, if that's discrete, a conditional model is sometimes called a discriminative model, because it lets us discriminate between the different possible values of the y variable. So by far, the most common conditional model is a linear model. And that model looks like this, right? We have our variable y that we're trying to predict, and we say that it's approximately equal to y hat, which is a linear function of x. So it's x times w plus b, where w is the slope and b is the intercept of our linear function. So that looks like this, right? So we have our x variable on the horizontal axis, and the prediction in red, excuse me, we have the prediction in red, which is just a linear function of x, and then the actual value of y has some noise that separates it from the red line, but you can see it's a pretty good prediction. So estimating w and b from data is called linear regression, and we're going to talk now, like I said, about univariate linear regression, meaning a single input and a single output, just like what's in this graph. All right, So to fit our model, we need a sample. A sample is just a set of data points that are drawn IID from the joint distribution of x and y. Sorry, somebody's asking for more detail about the CDF transformation here. And I think they're asking about this step where we ask why does f of x follow the uniform distribution? Right. So, or sorry, why does f inverse of u follow the distribution f of x, right? And that's basically, I mean, this derivation shows it, but I'll go through it again. So, so we have our variable x, which is defined to be f inverse of u, right? So this is showing that if we have a uniform random variable, we can compute f inverse of u, and we'll get a random variable that has the given CDF f. And so how do we know that it has that given CDF? Well, we can calculate its CDF. Its CDF is just, for any given cutoff little x, what's the probability that x is less than or equal to little x? Monotone transforms don't affect the order of an inequality, and so x less than or equal to little x is the same as f of x less than or equal to f of little x. F of x, right, is by definition equal to u. So this is the same as the probability that u is less than or equal to f of x. And so this probability, right, the probability that a uniform random variable is less than or equal to some number p is just p, right? For any number p between 0 and 1, by definition, a uniform random variable has probability p of being less than or equal to p. And so this is equal, the p of probability that u is less than or equal to f of x is just f of x. And so we've shown that the CDF of x, where x is defined this way, is equal to just that function f of x, the desired one. And so that means that we can go back and forth by making this CDF transform. We can go back and forth between a random variable of any desired distribution and a uniform random variable. Right? This shows one way. It shows the way of going from uniform to the desired CDF. But if you just apply capital F to both sides of this equation, you see that you can go the other way. Take x, and then f of x will have a uniform distribution. All right. So back to regression. So in order to fit a regression, we need a sample. A sample means just a whole bunch of pairs that are drawn from the joint distribution of x and y. These are identically distributed, meaning each one is drawn from that distribution, and ideally they're independent. You can actually work with them if they're not completely independent, but for now let's just assume that they are in fact independent. So this is the same type of data that we would use to fit a joint model, right? We could fit a model of the joint distribution P of xy, given a sample from that joint distribution. But hopefully when we fit the conditional model, we're able to use a smaller sample size, for example, to get good performance. Let's see. So what's the purpose of trying to transform a random variable to be modeled by a different distribution? So if you had a random variable that was not modeled easily by any one of the sort of common families of distributions, then you could transform it so that it's modeled by one of the common families, and then it becomes easier to work with, right? So if you take a random variable that isn't normal and you transform it so that it is normal, then you can use all of the tools that people have developed to model normal random variables. And so it can be very convenient to have it in the original, have it in a space where it's a normal random variable. If you wanted to predict, of course, like if you wanted to generate samples from the original random variable, what you could do is you could generate normal samples and then apply the inverse transformation to get back to the original random variable. All right. So, all right, so suppose that we have our sample, right, written this way. So just as a notational convention, I'm going to put index within the sample as a superscript so that I can talk later when we talk about multivariate regression. I can use subscripts to indicate which of the components of a particular vector we're talking about. So x2 and y2 with a superscript 2 means the second one of our IID sample. And so given this sample, we can fit the best line by minimizing errors, right? So we're going to call zi to be the difference between yi and our prediction y hat I, right? The prediction of zi, the prediction of yi. So for example, if we predict 3 and it's really 4, the residual will be +1. Whereas if we predict 4 and it's really 3, the residual would be -1. And so to minimize these things, what we're going to do is we're going to define some function little l, script l, that has a minimum at 0. So we would like, 0 is the best possible value, right? And then it's sort of bowl-shaped. It goes up when you go away from 0. And then we're going to minimize the sum over all examples of the loss function applied to the residual, right? And so this function L is clearly minimized when all of the residuals are 0, and so that's the case we're trying to get to. And then expanding out the definition of zi, that's L of yi, the true value, minus the predicted value, xi times w plus b. And most often, we'll use the squared loss. Minimizing squared loss is called least squares. We've seen that before. But it's also perfectly reasonable to do regression with other loss functions, like, for example, the absolute value of the residual. And then once we're done, once we've found the values of w and b that minimize this loss function, we can report the minimal value of L to say how well we've done at fitting the data, right? So if we go right through all of our target points, we get a total loss of 0, whereas if we miss them wildly, we get a big loss. And people will report the total loss, or they'll sometimes also report the average loss, right? So divide by the number of data points. For squared loss, the sum of squared residuals divided by the number of data points is called the mean squared error. And the mean squared error tells us typically for a typical data point, how much do we deviate from, does the prediction deviate from the true value? So more precisely, we are estimating the variance of the residual using this mean squared error. It's also common to report the square root of that, because the square root of a variance is a standard deviation. And so an estimate of the standard deviation of the residuals is the square root of the mean squared error, also called the root mean squared error. So why is squared error so common? The answer is, well, there are a couple of answers. One is just that squared error is really convenient. We'll see later that the algorithm for minimizing squared error is pretty simple. The other is that if you assume that the conditional distribution of y is Gaussian, given x, then squared error turns out to be the natural loss function. In particular, it turns out that if you do maximum likelihood, assuming that y's conditional distribution is Gaussian, then you get squared error. Now, a lot of people just start by assuming, like when they introduce linear regression, they start by assuming this linear Gaussian model that y is a linear function of x plus a Gaussian residual. That is completely unnecessary. Regression makes plenty of sense even when your residuals are not Gaussian. And it's very useful in that case. For example, people often use linear regression in the case where y is binary, either 0 or 1. And clearly the residuals are not Gaussian in that case, but linear regression is still very useful. All right, so let's go ahead and derive then that the MLE for the linear Gaussian model is the least squares solution. So the log likelihood, right, L is just the sum over training points of the log of the joint probability. We can split that up using the chain rule into the log of the marginal of x times the conditional of y given x, right, and then split up that product into two logs. And then using the linear Gaussian model, we can get that this term, the first term, the conditional probability, is a normal distribution with variance sigma squared, right? So you get 1 over 2 sigma squared, and mean xi times w plus b, so you get y minus xi times w plus b squared, right? And then you get the normalizing constant, or the log of the normalizing constant for a normal distribution, which the normalizing constant is 1 over the square root of 2 pi sigma squared. So the log of that for n different terms looks like this. And then you get some constants that don't depend on our parameters w, b, and sigma, right? So the entire probability of x is constant because we're assuming that it doesn't depend on w, b, or sigma, and then you can get potentially other constants from the normalizer. So in fact, because this log p of xi term goes away, people often just don't bother with it. They start by just trying to maximize the sum of the logs of conditional likelihoods, and that's called maximum conditional likelihood estimation. And we just proved that that's equivalent to maximum likelihood estimation under the assumption that our marginal for x, the input variables, doesn't depend on our parameters. All right, so when we maximize this likelihood with respect to w and b, this factor 1 over 2 sigma squared doesn't matter, and neither does this additive term here that depends on sigma. And so that means that it's equivalent to maximize L or to maximize just this the sum in the first term, which is exactly least squares. So we've shown that maximum likelihood in this linear Gaussian model gives you exactly least squares. But again, you don't have to assume a Gaussian model in order for least squares to be useful. All right, so we're going to take a look soon at the solution of the least squares problem. But in order to avoid a whole bunch of extra ink in our math, we're going to make a simplifying assumption, which is that we're going to center our variables. That means subtract off the mean of each variable from the variable. So we replace xi by xi minus x bar, where x bar is the mean of x, and we replace yi by yi minus y bar, where y bar is the mean of y. And when the mean is 0, it's called centered. And this is no loss of generality, right? Because any sample, we can compute the mean and center it. We're just we're doing it to simplify notation later. And the reason it simplifies notation is that it just lets us drop the intercept term, right? So if we take, here's our loss function, the sum of yi minus y hat I squared. And if we differentiate that with respect to b, we get that when we set that derivative to 0, we get that b is 0, right? So I'm not going to go through the derivation because it's very similar to a bunch that we've done before. But if you go through it, you find that at the optimum, the intercept term is 0. So if we centered our data, we then have to uncenter our data in order to make predictions, right? So in general, there are a whole bunch of things we might do to pre-process our data before we fit a model to it. And if whenever we do these pre-processing steps, it's important to do the corresponding pre-processing steps on the test data, right? When we have to use the model to make predictions, we have to compensate for the effect of our pre-processing steps. So in particular, we can compensate for this one, for centering, by just changing the intercept term, right? So we start off with the intercept term being 0. And then we fit something that says y minus y bar is a linear function of x minus x bar. And if we want to, then we can move all of the terms that don't involve x over to the right-hand side. That's this one. And so here, right, if we just set b to be these terms that we, these constant terms, then we can make predictions of y instead of y minus y bar. Now, a common mistake when people are working with pre-processing steps, when you're working out your pre-processing, you have to do it on training data only, right? In other words, if your pre-processing depends on your test data, you're not going to be able to make predictions because you'll need to know your test data ahead of time in order to figure out your pre-processing step in order to make a prediction on your test data. So you have to make sure that whatever algorithm that you use for figuring out your pre-processing step only depends on the training data. So in this particular case of centering, that means that you use the mean of x on your training data and the mean of y on your training data. And then that will let you predict on your test data by taking the x for your test data, subtracting x bar, which you calculated on the training data, multiply by w to get a prediction of the centered version of y, and then adding back in y bar, which you computed on your training data, in order to get a prediction for your test data. Now the mistake, right, so if you're making predictions, you won't make this mistake because you just don't have the test data available when, until after you've made your prediction. But a common case that people do make a mistake is when you're trying to evaluate the performance of your learned model. So in particular, what people will often do, we'll talk about this more later, is they'll fit their model, they'll split their data into two parts, calling them training data and test data, and they'll fit the model on the training data, evaluate its performance on the test data, and say, oh, if I'm doing well on this test data, then it must be a good model. But if you use something about the test data when you're computing your model, and your model includes all of the pre-processing steps, then you're effectively using the test data to make predictions about the test data, and that's going to give you, that's unrealistic because you wouldn't be able to actually do it in a real case of making predictions, and it's going to give you the wrong answer. So if you let information from the test data contaminate your model, then your model could potentially just take that information that you put into it from the test data and spit it back out and give you right answers even though it hasn't actually learned anything. Let's see. So somebody's asking, why is centering necessary for minimizing least squares? It's not necessary. So the only reason we're centering is to make the math simpler in the derivations that we're doing. It's a convenient pre-processing step, and it is in no way necessary. If you want to avoid the centering step, you can just do least squares with both w and b as separate terms, and so you can do that, and the equations are just a little bit longer, a little bit harder to follow. So we're doing centering for convenience. So let's see. Somebody's asking me to repeat the material about squared error being, so if we go back up here, right? If we assume that the conditional distribution for y is Gaussian, whose mean is a linear function of x, right? So that's called a linear Gaussian model, right? The linear Gaussian model says that you take your x, you multiply by w, add b, and then add some Gaussian noise, and that gets you y, right? So that model, that's called the linear Gaussian model. If you assume that model and you do maximum likelihood in that model, you will get that the maximum likelihood problem is equivalent to doing least squares. So that's what the derivation in this section 5 here is. And so least squares is strongly related to this linear Gaussian model. And that was the point that I was trying to make. They're not the same thing, right? You can do least squares even if you don't believe the linear Gaussian model. And you can fit the linear Gaussian model by methods other than maximum likelihood. And so, you know, they're not the same thing, but they're strongly related. All right. So, all right. So we just finished talking about this paragraph 7 here in the lecture notes, which basically says, just a reminder, whatever you want to do to make your predictions, you have to figure all of it out from the training data only. Otherwise, when you go to make predictions, you won't be able to if you don't have access to the test data. Or if you do have access to the test data, you're going to be effectively cheating by looking at the test data in order to make predictions. Okay. So let's solve to find the optimal slope in least squares. Right. This is actually a special case of a derivation that you've seen before, but it's kind of instructive to see what it looks like in the univariate case. So if you take your I mean, this actually works for this derivation actually works for multivariate, but let's go through it just pretending that everything is univariate. So the loss function, oh, I'm sorry. This derivation, the way it's written, does in fact assume univariate. So let's take capital X to be a vector which stacks all of our training examples, right? So each one of our training examples has a single real number for X, and we stack them. So we have, if there are n training examples, this will be a vector of length n. Same thing for Y. So now we have two vectors, X and Y, one of which is the inputs and the other of which is the outputs. And we've assumed that they are we've assumed that they're centered, so that we only have to fit this W parameter. So then our squared error is going to be the squared norm of the vector y minus x times w, right? So in other words, x times w, what that does is it takes each one of our training inputs and it scales it by the same amount w, and then subtracts it from the corresponding y, and then we square it. Right? And so if we expand that out, that's y transpose y minus 2y transpose xw plus x transpose x w squared. And so if we differentiate and set to 0, right, we take the first term, y transpose y, has no w in it, so it vanishes. Y transpose xw, its derivative is just y transpose x. And x transpose xw squared, its derivative is x transpose xw times 2. And the 2's in both of these terms cancel with the half in front. So we get that the dl, which we're going to set to 0, is equal to minus y transpose x plus x transpose xw times dw. And so if we solve for w, we get that w is y transpose x over x transpose x. And because we've assumed that the means are 0 for x and y, x transpose x is just n times the variance of x, and y transpose x is just n times the covariance of x and y. And those two n's cancel, and so we get that the weight is the ratio of the covariance of x and y to the variance of x. So in one dimension, in a univariate linear regression, the least squares slope is proportional to the covariance between the inputs and the outputs, and it's inversely proportional to the variance of the inputs, right? So that's actually kind of a nice interpretation. It tells you that by measuring these sort of understandable quantities, the covariance and variance, we can get the slope of the optimal regression line. Now we can make this even more intuitive by scaling our inputs and outputs. So if we scale x or y, we'll equivalently scale w to compensate. It's just, scaling x is like stretching the entire plot horizontally. Scaling y is like stretching the entire plot vertically. And so, for example, if you multiply x by k, that will scale w inversely by k. And then if you scale y by k, that will scale w by k, because you want to predict something k times as big. And so, here's some pictures, right? If we scale x and y so if the original x and y are on the left, we could scale y by multiplying it by 2, or we could scale x by multiplying it by 2. And we would get the same linear relationship, just with a scaled slope. And so because of that, we can standardize. Standardize means making the mean 0 and variance 1. So our mean was already 0. So in order to get standard deviation 1, we divide by the observed standard deviation. And so when x and y are standardized, the variance is 1. So that term, right, so if you go up here to the expression for the optimal w, the variance will be 1, so that just drops out. And covariance is the same as correlation when the variance is 1. And so you'll get that for standardized x and y, the optimal w is the same as the correlation between x and y. So this is like a nice interpretable way of thinking about linear regression, is that the slope of the linear regression line is exactly the correlation between x and y, if x and y are standardized. And if they're not, you just take the correlation and you scale it to compensate for the scaling of x and y. And then the same thing, you can undo the centering as well, and that just means that you shift the intercept to compensate for the lack of centering. All right. All right, so that is univariate linear regression. In practice, there are a few problems that you should watch out for if you're trying to apply linear regression. So they work quite well, even for, even when the linear Gaussian model isn't exactly correct. There's 3 main problems that are likely to trip you up in practice, which we can go through one at a time. They're called outliers, heteroscedasticity, and nonlinearity. So if the conditional distribution of the residuals is heavy-tailed, right? So I'm talking now about, for a given value of x, if there's a significant probability that y will be way off of what you would predict with the linear model, then what's going to wind up happening is that you'll see a small number of points where the residuals are just really huge. So not necessarily, it could be a fraction 1% or 5% of your points, and it's still enough to, potentially cause problems. So if you have these outliers, they unfortunately can dominate the result of least squares, because basically the squared residuals, residual squared gets large really quickly, or comparatively quickly as the residuals get larger. And so that means that, if you have, if your loss function is sort of bowl-shaped like this, then small residuals down here at the bottom part of the bowl, they don't affect your loss that much. But if you go out to the sides of the bowl where it's pretty steep, your residuals, those big residuals, can influence your fit a lot. And so what that's going to wind up doing is you'll have, so if you have, here are some points, right, and we'll make a fit to them that looks something like this. And then if we have just a single point, if we add a single point, let's say here, right, so that has a really large residual, then what's going to wind up happening is it'll have an outsized influence on the fit, and it might change it to look something like that. So we'll talk about how to fix that in a sec, but that's the outlier problem. All right, even if outliers are rare, you could have that the different, depending on x, the variance of y could change. It could be small variance when x is near 0 and large variance when it's not. So distributions with different variance are called heteroscedastic. And if you're in the heteroscedastic case, you get a problem that's actually kind of similar to outliers. Places where the conditional distribution has high variance, they'll tend to dominate the fit, and you won't pay much attention to the places where the variance is low. And then last, if you have a nonlinear relationship between your variables, you're going to wind up, well, the linear fit is not going to be perfect. There will be some places where it's where your fit is biased upward and some places where it's biased downward. And so what you would really like to do is take account of the nonlinearity, and we'll talk about how to do that in the next set of notes. But it's important to know that nonlinearity will sometimes look like outliers or heteroscedasticity. In other words, if you have a function, if the expected value of y given x is really a nonlinear function of x, then it could appear that you have some really large outliers. And those are places just where the nonlinearity moves the true expected value far away from the best fit line. So how do we diagnose these problems, right? It's important, if we are worrying about these problems, to be able to tell when they're going to happen. And again, a plot is the answer. So if we make a scatter plot where the horizontal axis is our prediction, y hat, and the vertical axis is our residual, z, so y minus y hat, that's called a residual plot. And so here's an example of a residual plot where there's clearly something wrong, right? So if you look, when we're predicting -1, right, we're typically under-predicting. The actual value of y is higher. And if we're predicting +1, right, we're typically over-predicting. The actual value of y is lower. And in the middle here, when we're sort of neither under-predicting nor over-predicting, we're still getting lots of extra variance, right? The variance of the true value of y is much bigger in the middle of the plot than it is on either side of the plot. So there's an example where a scatter plot helps us diagnose a problem. So this particular scatter plot, what it's showing us is that there's some nonlinearity happening, because you can see that there's there's a bias in the value of the true value of y depending on where the predicted value of y is. You can also, it also shows, for example, heteroscedasticity, right? This the variance of the residuals is different at different points in the plot, and some outliers, right? Well, not very bad outliers. Just a value of -1.25 is not very bad, but they are there are a few values where y is quite different from y hat. Oh, somebody would like a sketch of heteroscedasticity, so that's easy. So plain heteroscedasticity would look like this, right? So the plot over there shows several problems at once, it looks like. But if we have a, here's our line, our best fit line, and let's say y is quite close to the line over here, but then as we come over here, the variance of y is much larger, right? So it's like that, maybe. So if you drew a line showing the standard deviation, right, it would look like that. All right. So residual plots work equally well for univariate and multivariate regressions. So we'll come back to them again later when we talk about multivariate regression. All right, so once we've diagnosed the problem, we want to fix it. And depending on what we've discovered as the problem, there's a bunch of different ways to try and fix it. So to fix outliers, right, the first problem that we could detect is that there are some outliers. There are a few different sort of common ways to try and fix outliers. So way number one is to use a robust loss function. So a robust loss function is something like the Huber loss, which is defined in the notes here, which looks like the Huber loss looks like this, right? So Huber loss looks like x squared for the first part, but then it just starts going up linearly instead of quadratically, right? So I guess I should label this is heteroscedastic, and this is the Huber loss. So why is that important? Well, we said that the reason that outliers were so influential in a least squares fit is that the squared error goes up really quickly when you get far away from zero, from a zero residual, and so the Huber loss, it just goes up slower, and so it's less affected by the residuals. Now, of course, the residuals are still there. They're still influencing the fit. And so you might do even better if you could remove the residuals. We don't know ahead of time which points are residuals and which points aren't, but there's a really simple heuristic that works pretty well when there aren't a lot of residuals. And that heuristic is to fit a line and then look at the points with high residual and remove the points with highest residual. And we can do this over and over again. So after we've removed a few potential outliers, we refit. And because the outliers have such a big influence, our fit might change substantially. And so it'll change which points are considered outliers. And now we can sort again and remove the top, percent of the most outlying-ish points. And we do that until we decide that we're good. And this works well as long as the outliers aren't really huge or really common, right? Because if you completely mess up your regression fit, you're going to be removing points effectively at random. It works even better the slower you go, right? So you can remove, the best is to remove just one outlier at a time, but then that would waste a fair bit of computation because you have to keep redoing the least squares fit. And of course, you need to decide when to stop. And a good way to stop is to use, for example, a QQ plot to compare your residuals to a normal distribution. And if there's evidence that your residuals are fairly far from a normal distribution, you keep removing outliers. Another good way is cross-validation, which we haven't gotten to yet, but we'll talk about it later. And once we've done that, we have at the end an outlier detection rule. We've removed, let's say, all points that are more than 3 standard deviations away from the prediction. And so that lets us decide for a new test point. We make a prediction, and if we're way off, we say, oh, well, this was an outlier, and we count it in one bucket. And if we're fairly close, then we say, oh, okay, it wasn't an outlier, it's an inlier, and we'll count it in another bucket. And so it helps when you're evaluating your classifier to separately say, well, you know, we have this fraction of outliers, and then on the inliers, the mean squared error is this much, right? And it's a trade-off. By declaring more points to be outliers, you can get a better mean squared error. But of course, you know, you don't want lots of outliers and you want a low mean squared error. And like before, we have to determine our cutoff for what's called an outlier using the training data only. Otherwise, we'll get misleading answers when we apply it to test data. All right. And so if we are heteroscedastic or nonlinear, the fix is basically to transform our data to try and reduce it. So for example, if our, let's say our variable x is always positive and the variance gets bigger as x gets bigger, well then we might want to take the log of x, right? Because what that'll do is it'll reduce the variance let's say that y is always positive, and the variance of y gets bigger as y gets bigger. Then we might want to take the log of y, because then the log of something, its variance, you know, if like the log tends to squash together large values of y, and so it'll reduce the variance in the case when y is large. Similarly, if you think that something's nonlinear, then, well, you transform your data to try and get a better fit with a linear model. And we'll talk about that more in the next set of notes. All right, so that is univariate regression. Univariate regression is really quite an incredibly useful tool. In some sense, it's the simplest machine learning model, and while we are more than happy to teach you more complicated machine learning models in all of the many courses that the machine learning department offers, one of the secrets that a lot of people don't realize is that you get, in many cases, you know, 80% of the performance with a linear model at almost no effort, right? And so, I mean, in some cases even, just a linear model is the best model, right? Maybe, you know, we teach you all of these complicated models for the cases when a linear model isn't good enough, but in maybe 80% of the cases, a linear model is actually all you need. And so you can go, you know, you can go and cause quite a bit of damage in a prediction task by just applying a linear model. All right. So please keep asking questions about univariate regression, but I think now it makes sense to move to multivariate regression. So there's two ways in which a regression can be multivariate. Our input variable x could be multidimensional, and our output y could be multidimensional. And those lead to, I mean, they both lead to needing to deal with vectors and matrices, but they have, you know, slightly different properties. But they're similar enough that we'll just deal with both of them together. So we have now, our data looks like n different pairs of vectors, where each input is in Rp and each output is in Rd for some fixed value of p and d. So you might have like a 3-dimensional input and a 2-dimensional output, and so you'd have pairs of vectors. Xt is 3-dimensional and yt is 2-dimensional. And so then our linear function is instead of being represented by a scalar, it's going to be represented by a matrix or a vector. So in this case where y is two-dimensional and x is three-dimensional, a linear function would be y equals w times x, where w is a 2×3 matrix. And let's see, if y is just one-dimensional, w is going to be a row vector, right? And if x is just one-dimensional, but y is multidimensional, then w will be a column vector. And so you'll notice here that I skipped having an intercept term, and the reason that I'm doing that is, again, I'm just going to assume that everything is centered. All of our input and output variables have been centered ahead of time so that we don't need to deal with the intercept. All right. Let's see, so for the iterative outlier removal procedure, two questions. Somebody wants to know if it's going to converge. No, you can just keep removing the most outlier-ish point, right? And you'll just keep removing until you have no data left. But you can use a stopping rule like the one that I talked about, where you stop when the remaining distribution of residuals is normal, right, or fairly close to normal. Or you can stop using cross-validation. And then in iterative removal, do we recalculate the residuals after every iteration? Yes. After every iteration, we recalculate the fit, so our slope can change. And because the slope changes, our residuals will change. Some points that we weren't predicting well, now we might predict them well after we've done a few rounds of outlier removal. All right. So for multivariate regression, we have y equals wx, where now y and x are both vectors and w is a matrix. And by convention, I'm just making x and y be column vectors so that w, the matrix, multiplies x on the left to get y. And we can still find the best value of w, now a matrix, to minimize our total loss. Again, the most typical loss is squared error, and we're going to use that for the rest of these notes, but you can do Huber loss or absolute loss or any other loss function if you prefer. So we want to minimize the sum over all training points of the actual output variable minus the predicted, right, yt hat, the difference, the squared norm of the difference, right? And just substituting that y hat is wx, this is the sum over all training points of y minus wx norm squared, divided by 2 just to make the constants nicer later. So if we collect all of our data points into two matrices, right? So if we make a matrix X, which is the first column is x1, the second column is x2, and so forth up to xn, right? And then the same for y. We make a matrix y, which is maybe a different height, y1 up to yn, right, like that. So those are the matrices x and y that I defined here. And so if you write in matrix notation, the matrix y minus w times the matrix x, that's going to be equivalent then to this previous, that'll give you a matrix where every column is a residual. In this case, the residual can be a vector, right? It's the difference between y and y hat, and both of those are vectors, and so the residual can be a vector. And then if we take what's called the Frobenius norm squared of the matrix, so the Frobenius norm squared is just the sum of all squared entries of the matrix, then this matrix expression is equivalent to this vector expression that we used earlier. And then equivalently, using the trace, we can write that as the Frobenius norm is of A as just the trace of A transpose A, right? And so we can expand it out like this. And now what we've got is an expression that uses a bunch of matrices and then simple manipulations of the matrix. And then from here, this is a problem that we've seen before, right? We went through, in a couple of different contexts, the least squares problem for matrices like x and y here. And so I'm not going to go through, right? I've got the math for solving for w, but it's the same as the math that we've seen before. And the end is that we get that W times a matrix XX transpose is equal to a different constant matrix Y times X transpose. And so we can just solve this system of linear equations to get W. As we mentioned before, mathematically what we just do is multiply both sides by the inverse of XX transpose, but in practice that's actually a bad way to solve the set of equations. What you would want to do is do an LU decomposition of this matrix XX transpose, and use that LU decomposition to solve for the rows of W one at a time. An interesting point here that you can see this way is that each row of W is completely independent, right? So you can solve for the you can solve for each row of W in parallel if you want to on a completely different computer, right? All you have to do, like, it might make sense to pre-compute the factorization of XX transpose, but you don't even have to do that if you don't want to, right? Like, each computer could solve for a different row of W, and they don't even have to talk once they have the data. And so what that means is that if you have a multiple output regression, that's the same as having a whole bunch of different single output regressions. That's not true for inputs, right? Multiple input regression is you have to treat all of the inputs together, but multiple output regression, you can solve for each different output on a completely different computer if you want to. All right. So once we go to multiple variables in a regression, that opens up the idea of using feature transforms, which are really useful. So a feature transform is just a function phi that we apply to each one of our input examples. So we've used functions like this before, right? We used it in perceptrons in the first mini. We used it for talking about maximum entropy. This is a feature transform is the same as a vector of statistics that we would compute of each example. And so after the feature transform, we model that y is a linear function of phi of x instead of just a linear function of x. And phi can increase or decrease the dimension of x, so that would change the dimension of the required matrix of coefficients W. So just to give a little bit of intuition, an example might be a medical trial, where let's say y is a numerical measure of the severity of a patient's symptoms, let's say on a scale of 1 to 10. And x has two components. X1 is 0 or 1 depending on whether you've treated the patient with one medication, and x2 is 0 or 1 depending on whether you've treated the patient with a different medication. And so we could have a feature transform where instead of just using x1 and x2 as our inputs, we use x1, x2, and x1 times x2. And a feature transform like that would help us look for a drug interaction between these two medications. Right, so the coefficient of x1 says what is the change in the symptoms based on whether you've treated with the first medication. Same with the coefficient of x2 that says what's the change in the symptoms based on whether you treated with a second medication. And in the absence of this interaction term, x1, x2, you would predict that if you give the patient both medications, you would get the sum of the effects of the individual medications. And so if you add the interaction term, it allows you to look for a difference of the data from this prediction. And if you find one, you say that there's an interaction between the two drugs. You say there's an interaction effect. the coefficients of x1 and x2 are called main effects to contrast them with interaction effects. Another useful feature transform is to down select variables, right? So if you had a really high dimensional vector, you could try and throw away irrelevant components. And that would make potentially a more reliable model because you're not trying to, excuse me, you're not trying to fit the effect of an irrelevant variable. Of course, you don't know necessarily ahead of time which components of X are useful and which aren't. So the simplest thing to do is just to try, just manually try feature transforms that delete various ones of the components of X. And then there are automated algorithms which we might get a chance to talk about later. Things like lasso or forward stage-wise regression that are designed to automatically try and find the relevant components of X. So just as a matter of terminology, it's still called linear regression, even after we've made a potentially nonlinear feature transform. And the reason it's called linear regression is that the coefficient matrix W appears linearly, right? We're looking for a linear function. We can just pre-compute all of the feature transforms, and we don't have to worry about the fact that they were nonlinear. So effectively, all of the algorithms that work for the case without a feature transform also work for the case with a feature transform. So this seems like maybe a good place to stop. We'll continue on multivariate regression next time around. And look for, so we released a short problem set toward the end of last week, and look for us to release homework 1 fairly soon. We'll post on Piazza and Canvas when that happens. All right, my office hours start now, and we'll see you next time.